After this video, you will see much more clearly how a small detail on a drawing can turn into an entire operation chain in milling. Because in milling, the biggest cost driver is often not the amount of material removed. It is how many times you must clamp the part, which surface you choose as the reference, and how many measurements you are forced to insert between steps. Today we will look at milling not by asking can it be milled, but by asking when it is the right choice and when it creates unnecessary operational overhead. Milling follows a simple principle. A rotating cutter removes material from the workpiece while the part or the tool moves in controlled X, Y, and Z axis. This method is extremely strong for prismatic geometry rather than rotational geometry, flat faces, pockets, channels, shoulders, profiles, and contours. In machining centers, milling is rarely only milling. In the same setup, steps such as drilling, countersinking, stepped holes, and boring are often added to the chain. That is why milling acts as the backbone of the production flow for many parts. When should you choose milling? 1. Is the geometry prismatic? If the design is dominated by flat faces, pockets, channels, shoulders, and profiles, milling is usually the shortest path. 2. Do you need to control multiple surfaces in one reference? Machining multiple faces or features in a single setup carries parallelism, perpendicularity, and positional relationships more reliably. The real gain is often not speed, but fewer clampings and fewer in-process checks. 3. Is the whole pattern and positional accuracy critical? With the right fixture and the right reference strategy, machining centers can control hole positions more consistently. The key question remains the same. How many clampings? How many measurements? Process limits. Limit 1. Rigidity and vibration. Milling forces are intermittent, so vibration is easier to trigger. Thin parts, long overhangs, or weak work holding lead to surface waviness, dimensional drift, and shorter tool life. Limit 2. The inside corner reality. A milling cutter has a nose radius. Demanding a zero radius in an internal corner usually requires special tooling and extra operations. The design should allow standard cutter geometry whenever possible. Limit 3. Access and tool clearance. Narrow and deep pockets, as well as hard-to-reach regions, force you towards smaller tools. Smaller tools mean more deflection, lower feed, and longer cycle time. 3 typical mistakes in milling. Mistake 1. The habit of sharp internal corners. If function does not require it, relaxing the corner reduces cost and risk. Defining sharp corners only out of drawing habit silently increases cost. Mistake 2. Opening a large surface operation for a small need. For example, instead of machining an entire face just to seat a bolt head, a localized spot-facing operation is often a more economical solution. Mistake 3. The combination of blind and deep holes. In blind holes, chip evacuation and tool space become difficult. As depth increases, the risk of drift and breakage rises. If possible, prefer through holes. If a blind hole is necessary, use a bottom geometry that matches the reality of drilling and keep the depth reasonable. A 5-item quick checklist. 1. Design around standard tools. Choose channel width, radii, chamfers, and forms to match standard cutters whenever possible. 2. Add internal corner radii. Reduce the need for special tools and extra operations. 3. Leave tool clearance. Create relief at the bottom of shoulders, add end relief in channels, and ensure access space. 4. Think about hole entry and exit. Keep drilling entry and exit surfaces perpendicular to the axis when possible, and locate holes with a single consistent reference strategy. 5. Reduce operation count. Group features that can be machined in the same direction, and eliminate unnecessary second setups and in-process checks early in design. On milled parts, the most common GD&T topics are flatness, parallelism, perpendicularity, and positional tolerance for holes. For measurement, a caliper is useful for quick checks, while an indicator is a practical tool to detect surface and work-holding-related variation quickly. We will go deeper in the advanced training into tool selection, tool paths, tolerance analysis, and fixture design. If you found this video useful, please like, subscribe, and turn on notifications.